Thank you so much. It's an honor to present this workshop. Thank you for the opportunity. So over the next few minutes, I wanted to kind of provide you an overview of some of the work we did under SENTRY with focus on urban rail network deterrence with graph neural networks. And as we saw with the sabotage event during the Paris Olympics, transit systems may be potential targets during mass gathering events. And in order to deter adversaries from targeting such locations, uh, tools are needed that can incorporate the structure of these networks, in this case, rail transit systems, as well as that's essentially the topology or the connectedness of the network, its layout, and also the dynamics on these networks in terms of flow of people from various stations to others, and the cascading effects that can come about as a result of disruption in one location or multiple locations at the same time, in one region or multiple regions. So we need to be able to understand those parameters and those effects in order for us to be able to better characterize the risk and the deterrence aspects, and eventually inform resource allocation in a dynamic manner. And the solution that we worked toward was to essentially enhance the transportation security at such mass gathering events, which will enable even stronger protection of our critical infrastructure networks from various kinds of adversarial threat vectors. And the way we went about tackling this problem was to build a generalizable and a modular network risk modeling and simulation workflow, as well as software code, where we had kind of two key sort of modules. One focused on machine learning with graphs. So by graph here, I mean a network, which is comprised of nodes and edges. So node is a rail station, edges are rail lines that may connect various stations. And in this case, we were looking at the Boston Urban Rail network as our example proof of concept system. So what we did was essentially machine learning methods that are designed for graph structured data. And in this case, since our problem, our rail system is a network, so we want to apply those techniques that are suited for network structured data. In this case, specifically, we were looking at graph neural networks or graph convolutional networks. That's kind of an algorithm within graph neural networks that can allow us to provide and generate attractiveness predictions in terms of which stations are maybe more attractive, less attractive, relatively speaking, from an adversarial perspective, while capturing various aspects of the network, its the dynamics on the network, as well as changing properties of this network over a period of time. And then what we did was, using these predictions from the graph neural networks, what we ran was several tens of thousands of simulations of different kinds of cascading failure events to understand what are the best case, worst case scenarios, and all the scenarios in between, in terms of if a certain number of locations were targeted, how severe would that cascading impact result in fragmenting or disconnecting the network. And all of that can then lead toward resource allocation and prioritization, ranking of various locations, which, by the way, can also change with changing conditions. So be able to provide such dynamic ranking and generating lists like that can be useful for various kinds of resource allocation activities. Currently at a technology readiness level of 3. So we have a proof of concept software tool that we have developed for demonstration. And with the additional effort, we hope to move toward a TRL4, closer toward technology ingestion. Of course, we have to work closely with our Homeland Security enterprise stakeholders to get to that next level of maturity. Next slide. And I have a series of kind of pictures in the next few slides, snapshots, screenshots of various aspects of the work. So I'll kind of touch on them briefly, and of course happy to answer questions at the end. So we first kind of started out by looking at global terrorism events targeted at rail infrastructure. This is data from the Global Terrorism Database. From the START Center at University of Maryland. And what we notice here, of course, from the data set ran from 1970 to 2021. And so there are lots of events targeted at rail infrastructure globally, but of course, not as many events captured in this data set, within the US. And of course, if we zoom in further in the Northeast, we have a smaller number of such events, thankfully. But there's data out there that we can kind of draw from, learn from in terms of events that have happened historically in other places around the world. Slide. And then sort of before we jumped into the technology, the development aspect, we wanted to sort of also tease out some of the key characteristics of what specifically contributes toward us understanding further urban rail network threat deterrence. And many previous speakers have already kind of mentioned and alluded to that. We want to be able to capture different kinds of effects, right? All the way from this notion of threat shifting, where if we harden a certain location, of course, adversaries or threat might shift to other locations, as we saw in the case of Paris 2, where Paris was hardened, but the sabotage events occurred at places one step away from Paris or one station away. There is also a notion of disruptive node failure sequences. Maybe certain sequence of failures can lead to more catastrophic fragmentation of the network than other sequences of failures. So where they might reside is important for us to be able to capture. At the same time, we want to look at operational ridership. So there are certain stations that we know are busier during certain times. So that kind of maybe contributes towards its exposure as well as sensitivity to various kinds of events. There is also crime. And in this case, looking at the Boston Rail Network, there are certain neighborhoods that have higher crime. So, that may play a role as well in terms of certain areas being less guarded or more guarded by default. And then how that can play into, whether that particular stations in those locations are, more attractive, less attractive from an adversarial standpoint, as well as resource prioritization in various regions, various options that are available. So there might be criteria and priorities that need to be taken into account. So all of these factors collectively contribute toward us sort of getting a better handle on the deterrence problem and the network risk problem. Next slide. And then this is just an overview of our workflow, the technology sort of stack, how we kind of went about developing our proof of concept tool. So, we used open source data. So from data collection to a multi-criteria decision analysis approach to identify various, node feature embeddings. Node here again is a rail station, which was then sort of subject to a machine learning with graph module, where we used graph convolutional networks to predict node target attractiveness from an adversarial perspective. And based on those attractiveness scores, as well as other network properties, we ran various network failure simulation and analyzed the fragmentation of the network as a result of those failure sequences. Along with the machine learning approach, we also developed explanations of why we saw certain predictions as a result of various combination of initial conditions. So that way we can be more explainable and transparent in terms of how the machine learning method arrived at various outcomes. Next slide. And here's just a sampling of results. This is looking at the predictions at various time windows. These are sort of 9 time windows defined by the Massachusetts Bay Transportation Authority, as sort of from very early in the morning to late at night. And we can kind of start to see how various stations color coded based on these attractiveness predictions. And some places are maybe more attractive from an adversarial perspective than others at different points in time. So this is the kind of information we can kind of then utilize to be able to make resource allocation decisions as well as prioritization exercises. Again, there is spatial and temporal variabilities are captured here. Next slide. And this is sort of a graphic showing, basically each sequence here. This is the result of failure simulations. In this case, we were looking at, what if there were four locations that were to be impacted if they were impacted. Similar to, in Paris, there were 4 locations that were impacted. So if in this case we were looking at Boston Rail, so which sequence of 4 stations, like in what order, would result in the maximal sort of fragmentation of the network. So the top here is the best case, the bottom here is the worst case. And we looked at different criteria based on centrality features, as well as various attractiveness predictions at different times of day, like AM peak hour, PM peak hour, so on and so forth. So we can get kind of a full spectrum of different what if scenario analyses, and then we can kind of draw from here which stations, in what order may lead to maximal disruption, so we can accordingly protect and harden those locations. Next slide. And here are some sort of screenshots from the tool itself. So this is sort of a visualization page where we can visualize global terrorism events. This is from the Global Terrorism Database. Next slide. Here we look at the ability to, again, geospatially visualize the Boston Rail urban rail network, and then in this case we were overlaying sort of the crime heat map on top of the Boston Rail network. Next slide. And this is an example of looking at various rail network centrality features. For example, eigenvector centrality is one sort of type of centrality feature which sort of assigns higher scores to nodes that are close to large locations. So, for example, in the case of Paris, neighboring stations would get a high centrality value. So in this case, we're looking at the same idea, but applied to the Boston Rail Network, and this can identify some stations that have a higher score, lower score, might be important for us to consider. Next slide. And here's an example where we're looking at ridership information, again, time-stamped. So we can kind of see which stations become more important, more busy. So sort of level of busyness, which can also be a key factor in sort of understanding where to mobilize resources at what point in time. And next slide. I think this is my last slide, where again we were looking at this is a notional sort of defense posture, where in this case we were looking at spatial proximity to various facilities such as police stations and hospitals, and closer they are to certain locations. Again, we're making an assumption here. Maybe they are better. There's a higher chance of low response times if something were to happen. But of course, we need to work closely with the Homeland Security enterprise stakeholders, as well as law enforcement and transit authorities, to sort of better mature some of the capability and the technology proof of concept demos that we have developed so far. Thank you again, and happy to answer questions.